Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at ECE and RBCCPS IISc. Today's talk is by Professor Sandip Chakraborty, and he will be speaking on RF Beyond Communication, New Opportunities for Human Sensing with mmWave. Professor Chakraborty is an associate professor in the Department of Computer Science and Engineering at IIT Kharagpur. He obtained his Bachelor of Engineering degree from Jadavpur University, Kolkata in 2009, MTech and Ph.D. degrees from IIT Guwahati in 2011 and 2014 respectively. The primary research interests of Sandip Chakraborty are on various aspects of computer systems and networks, and the development of assistive technologies for social well-being, and the design of distributive, pervasive, and ubiquitous technologies over mobile devices and smartphones. Professor Chakraborty is leading Ubiquitous Network Systems Lab at IIT Kharagpur, focusing on various aspects of ubiquitous and pervasive sensing systems, along with the computer-human interaction. He is leading multiple high-valued projects sponsored by the Government of India, India, as well as various industries like Intel, Oppo, HP, TCS, and BEL. He is one of the founding members of SEM iMobile and the SEM SIG-Mobile chapter in India. He is an area editor of Elsevier Ad Hoc Networks Journal and Elsevier Pervasive and Mobile Computing Journal. He has received various awards and accolades, including INEAE Young Engineers Award, Fellow of National Internet Exchange in India, and so on. Further details can be about his work can be found in his website. I'll be pasting the link. Before I move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may raise your hand and ask Professor Chakraborty directly. Over to you, Professor Chakraborty.
Thank you. Thanks for the detailed introduction. And very good afternoon to all of you. I'm happy to give a talk today on the current research activities that we are doing at Ubiquitous Network Systems Lab at IIT Kharagpur. So just before I start the topic, I would prefer to have the talk as much interactive as possible. So whenever you have any doubt or have your question, any kind of question, feel free to ask it. Feel free to unmute yourself and poke me for the questions. So today, I'm broadly going to talk about some of our very recent work on using pervasive sensing technologies for understanding human activities. So we'll see that how our next generation mobile phones can be equipped with not only a kind of high communication speed, but with kind of huge sensing capabilities that can be leveraged for multiple different interesting applications. Now, just to start with, to give you an example of the type of situation or scenario that we are talking about, just think of that you are in an environment, you are in a room, and the room can understand you. The room knows you well. That means it can find out what type of activities you are doing. And say, for example, when you require some specific support, when you require, say, a silent area, and so on. And accordingly, that smart room can respond to your requirement. Now, for this, to realize this kind of vision, the important thing that we need to keep in mind that we need a sensing system through which we can understand a large modality of activities that a person is doing within the room, right? So that can involve doing exercise, even typing on a laptop, doing cooking, doing certain exercise, sleeping, and so on. There can be a plethora of large number of activities that a person can perform within a room. Now, this kind of sensing, like sensing the human, that particular idea is not very new. Rather, there have been decades of research on understanding human activities. People have looked into different source of data, like understanding the gesture that the person is performing, looking into the vital signs of individual, the movement pattern, the location. Then different types of sensor modalities have been utilized for this purpose, like the vision, Bluetooth, Wi-Fi, RFID, different kind of active and passive sensing techniques, like putting up a smart band, and from that smart band to understand that how many miles you have walked or how many miles you have cycled. And this kind of sensing data that you are gathering, typically we apply feature extraction mechanism, like apply techniques like signal processing, analysis, or various kind of deep learning techniques to build up a model to infer various kind of application scenarios, like understand the speech, understand the position of the user within the room, monitor the vital signs like the breathing rate, understand the facial expression, understand the gesture, localization, tracking. So these kind of things have been well explored in the literature. And as I was mentioning that people have explored different types of modalities for this purpose, ranging from acoustic signals, ultra-wideband, Wi-Fi, millimeter wave-based communication, Bluetooth, LoRa, and all of them has their own properties. Like all these different signals, they work in different frequency range. Some of the signals, they are affected by external interference. Some of them have low range resolution, less accurate, or sometimes it can sense up to long range, but doesn't work good in an indoor environment. Now, considering all these different kind of sensing modalities that we have, in today's talk, I will particularly focus on this millimeter wave sensing, which is, I think, many of you know that it is going to be a part of our 5G communication, to utilize this millimeter wave band for doing the communication, which works in roughly within 30 to 300 gigahertz band. And there are various commercial device, prominent technology, which are likely to be available in the near future. And considering that, we see that, well, while these communication people are exploring millimeter wave for wideband communication, can we also utilize millimeter wave for sensing purpose? And interestingly, in the last few years, there have been several works on even millimeter wave sensing, right? So people have tried to sense human, object, as well as the environment. Now, for human sensing, identifying the shape or gait of the user, tracking the position, monitoring the health-related things like the vital signs, sleep, disease, recognizing the user action, like head motion, hand gesture, body posture. Well, event detection, like whether a person is getting fall, some bathroom accident, presence, the pedestrian movement. So these kind of things have been well studied in the literature, and many of the aspects of human sensing that have been found out by utilizing this kind of millimeter wave technology. Now, the interesting thing is this particular slide summarizes different kind of sensing applications with different broad modalities, like sensing the breathing, heart rate, lip movement, eyelid movement, hand gesture, head movement, and with technologies like acoustic, both in the audible range as well as in the inaudible range, millimeter wave in different frequency range, the ultra-wideband, Wi-Fi, RFID, LoRa, and so on. So what we particularly focus on, we focus on this RF sensing part, which can seamlessly sense a human activity, because for Wi-Fi or acoustic, they are particularly prone to interference. So Wi-Fi will get interfered from the other Wi-Fi signals, and acoustic will get interfered from the different other devices which generate acoustic signals. So that's why they are not very good candidate for sensing, but what we believe that is RF signals like millimeter wave or ultra wideband, they can work as a good candidate for sensing. But interestingly, this sensing with higher bandwidth, it provides better range resolution and thus makes the sensing feasible. And that way, as I mentioned, that millimeter wave or ultra wideband, it provides higher bandwidth and becomes a very good candidate. But ultra wideband, it has a well-known issue of coexistence with other radio frequency. For example, it can work on a Wi-Fi frequency range. It has an overlap with the Wi-Fi frequency range. In that way, because it also shared the spectrum with other such technologies which are widely used for communication, so ultra wideband also get affected from the interference. And consequently, we focus on millimeter wave and we try to see that what exactly we can sense with the help of millimeter wave signals. Now, before I go to the broad group of applications that I'm going to highlight today, let me just talk about a brief background about this basic principle of millimeter wave. So we use the millimeter wave signals as a FMCW radar, which is broadly called as the frequency modulated continuous wave radar. With such kind of radar, we can measure the range of multiple objects which are there in front of the radar. So for example, I have a kind of, say, a radar here. And I have, say, multiple different objects in front of it. So what we can do that we can find out that what is the distance between the radar and the object. And that's the basic principle which is used to it FMCW. So it uses this concept of IF signal and IF bandwidth. I'm going to discuss about it in brief. And a broad idea of range resolution. So range resolution basically determines that up to what distance you can separate out multiple objects. Say, for example, you have two different objects here. So what should be the kind of minimum difference between these two objects so that this radar would be able to separate it nicely. So this basic idea of this FMCW radar, it works in this way. The radar transmits the charge signal. So the charge signal is a frequency modulated signal where the frequency gets changed over time. So as you can see in this diagram that the frequency is getting increased over time. So that way a charge signal, it is characterized by a frequency, the starting frequency, the bandwidth. Bandwidth means the maximum frequency that it can attain, and the time of the charge. That means for the time for which the signal is being transmitted. Now, what happens that whenever you are transmitting certain signal, because of this millimeter wave principle, it is sending the signal at a higher bandwidth. So the signal gets reflected from various reflecting surfaces. That can be the wall, that can be even the human body, any object that is being placed in the room. And this reflected signal is being received, and we apply a kind of modulator here to combine the transmit signal and the receive signal altogether. So it works in this way that you have a transmit signal, and this transmit signal get reflected from any kind of reflecting surfaces, as I mentioned, and you get a receive charge. Now, what we are interested in, we are interested in this frequency difference between this transmit charge and the receive charge. Now, the objects which are in front of the radar, they produces this IF signal, that means this difference, with a constant frequency tone. And this frequency tone can be characterized as S to D divided by C, where tau is the kind of round trip time. So what you do, that if you look into this IF frequency spectrum, you can find out a peak in the IF frequency spectrum at the position where a particular object is located, or particularly from the, say, for example, if there is an object here, from this object, the signal gets reflected, and you can capture that reflected signal, find out the difference between this transmit chirp and receive chirp, and this IF signal, if you plot the frequency spectrum of it, you will see a peak there that indicates the kind of presence of an object at this particular distance. Now, we use that idea to find out this range resolution. As I mentioned earlier, that range resolution is basically the ability to resolve two closely spaced objects. Now, when two objects are too close, they show up as a single peak in the frequency spectrum. So, for example, here, two objects are very close. That means the received signal will be very closer. And whenever you are computing the IF signal by subtracting the transmit chart with the receive chart, you will see a single peak. But if these objects are at sufficient distance, that means if I can increase the length of the IF signal, which also proportionally increases the bandwidth, then what we see that at certain IF signal point, we can see two different peaks corresponds to two different objects. And that way we will be able to separate out the objects very clearly. And that way, the idea is that if you have a higher bandwidth, you can find out a better resolution. So that way there is a kind of trade-off between the bandwidth that you are using and the range resolution that you can obtain out of it. So this is the kind of mathematical significance of this range versus bandwidth. And if you see some typical number, so for example, if you use 4 gigahertz bandwidth, you can have a 3.75 centimeter range resolution. Similarly, if you go in 60 megahertz bandwidth, your range resolution becomes 25 centimeter. That means if you increase your bandwidth, your range resolution becomes much more finer. That means with a 4 gigahertz bandwidth, if two objects are separated at a distance of 3.75 centimeter, you can clearly identify that. Whereas at 60 megahertz, your minimum distance between the two objects need to be around 25 centimeter. Well, so that means if you want precise movement detection, or if you want to separate out two objects which are very close to each other, then you need to use a kind of higher bandwidth. Now, another property that we are going to use for the IF signal is the phase of it. So, what we do that if you do a kind of Fourier transform of a sinusoid in the time domain, I think you already know that it produces a peak in the frequency domain, right? But the signal in the frequency domain is complex because it contains both the amplitude and the phase. Now, if you look into the signal corresponds to the transmit chart and the receive chart, you will see that there is a difference in phases between this transmit chart and the receive chart. And using that phase difference, if we look into this phase difference, we can actually identify the behavior of individual subjects which are in front of the radar. So that way, if we plot the signal matrix, then we'll see this kind of variation, which is basically what we call as the Doppler variation for the two subjects within this signal matrix. And this particular property we are going to use for subsequent analysis of this FMCW radar. Now, let us, well, before jumping to the problem, let me also highlight this idea of this angle of arrival estimation. This is another property that we typically use. It basically compute the angle between the transmit chap and the receive chap. So, for example, if I have a transmit antenna and a receive antenna, depending on their location, I can find out that what is the kind of angle of arrival for that signal. So, I'm not going to all these mathematical details because of the timing constraint, that just try to introduce with some of the terminologies like that range resolution and this angle of arrival, which we are going to use in subsequent discussion. So, the problem or the kind of applications that we are going to develop with this principle of millimeter wave sensing, I will broadly highlight two different applications today. One is this live monitoring and on-device inference of dangerous driving behavior, which is a work that got accepted in IEEE Parcom this year. And the second idea that I'm going to share with you in brief is about how we can do pervasive monitoring of multi-user activities at a room. So first, let us pick up this first problem about sensing and live monitoring of dangerous driving behavior. So the broad idea is something like this, that the inattentive driving is one of the common causes of road accidents, and particularly in India, we see that with this Ola, Uber, and different kind of cab companies where the drivers, many of the time, they do overwork, but they get fatigued and they perform kind of dangerous driving. They want to reach the destination early to reduce the travel time. So because of this multiple reason, there are severe kind of accidents that happen. So that way, one of the important thing is that whether we can monitor the attentiveness of the driver continuously while they are traveling. Well, now this again, monitoring this driver, this idea is not very new. Rather, there are many cars, or nowadays in many of these countries, even in India, in some places, it is important that people typically use a camera device on their car, which we call as the dash cam. So this dash cam, it has two different cameras. One camera is which is capturing the road, and another camera which facing the driver. So the camera which is facing the driver, using that camera, you can actually capture the activities of the driver and find out whether the driver is indulged in some kind of dangerous activities or not. And there are existing works, like there are works from Microsoft Research, which has used this kind of camera sensor to monitor the driving activities, like the project HAMS from the Venkat Padmanabhan's group at Microsoft Research. But one of the major challenge or major issue with this camera-based sensor is that, just think of that you are in a public car, you have hired an Uber. So obviously you will not like that you are being also captured by a camera that is being placed within the vehicle. Well, obviously this is privacy sensitive, and people will not like it to be captured through a camera. Well, maybe the driver doesn't mind, but the passenger might mind. So that way, these camera-based sensors are not very privacy sensitive. And what we thought of that, well, if whether we can have certain kind of alternate modalities to do that. And the idea is something like this, as I mentioned, that our next generation phones, the 5G phones, are likely to have this kind of millimeter wave-based communication. And whenever the driver is placing the phone in front of the dashboard, and we do it for multiple purposes, particularly for using the navigation and so on. Now, whether the millimeter wave signal that is being emitted by the phone, can it be used to monitor the activities that is being performed by the driver? So this kind of sensing infrastructure, first of all, it is compact, lightweight, because you do not need to do complex video processing. And you know that the video data is always a kind of heavyweight data. Even a few minutes of video, it eats up some MB or sometimes the gigabyte of these spaces, and you need to do complex processing on top of those videos. So what you can do, that you can use this lightweight processing. And also the most important thing is that this modality is much more privacy sensitive. You are not capturing anything about the passengers who are traveling, because they are at your front, and you can always adjust the range of this millimeter wave sensor depending on adjusting its configuration for range resolution. So this can be one of the very potential interesting application for this millimeter wave sensing. And here is the kind of deployment scenario that we have used. So here you can see that we have a dash cam here. So this dash cam is actually used for this ground truth. So here one person, he is holding a computer that is connected with all the devices. So here you can see the face of the driver is being shown. So this data we have just collected for this ground truth comparison purpose. But apart from that, we have a millimeter wave sensor which is being mounted here. Well, so this millimeter wave sensor, it transmits the chirp, and the IF signal you can see here. Now we basically do an analysis of this IF signal to find out whether the driver is indulged in some driving activities, in some dangerous driving movement or dangerous driving activities. Now, these are the kind of dangerous driving that we are going to detect. We basically classify the kind of activities in two different groups. One we call the actions which are being caused by drowsiness, like this nodding head, yawning, anomaly in steering, and also certain other actions which are caused by driving distraction, like the driver is drinking or eating something, turning back, picking up the drops, fetching forward, using the mobile phone while driving, talking to the front passenger or back passenger. So this kind of actions, which are typically considered as kind of distracted driving or dangerous driving, we want to see whether we can use mmWave sensor to do that. And just for your information, we have used this particular FMCW radar from Texas Instrument as a device for all our experiments. And what we see that if we keep the distance between the driver and the millimeter wave sensor is something from 0.6 to 0.8 meter, which is the typical distance between the driver and the corresponding dashboard. So this distance, then we can use this range pins from 6 to 16 in the range resolution to find out the driver activity. So 6 to 16, that means this part of the bin for individual sensing, that shows that whether the driver is indulged into any kind of activities or not. Now here you can see from this range resolution Range-Doppler heat map that for these individual activities, you have a different pattern in it. Well, say for example, the drinking, turning back, picking drops, nodding, they have a kind of different pattern. And interestingly, activities like fetching forward, then this PD means picking drops, then this turning back, this kind of activities, it shows a kind of circular pattern in the Range-Doppler heat map. Well, and on the other hand, the steering anomaly, in case of steering anomaly, the driver abruptly moves the steering wheel, that result in a sudden change in the Range-Doppler heat map. Well, so let me also show you the same with the help of some of the kind of screenshot videos that we have taken. So here you can see that the driver is going to drink the water, and just keep on observing this Range-Doppler heat map. So here, yeah, so the driver is picking up the bottle and drinking the water, and at this point of time, you see there is a change that has been observed in this Range-Doppler heat map. Well, similarly, in other activities, like when the driver is picking up something and looking behind, we also observe a similar kind of signature. So just I think the video is getting loaded. Yeah. Okay, so in the interest of time, I just can skip it because it is taking time to load the video. But what you can see, just like here, you have seen that there is some specific signatures that is being observed. So similar kind of signatures are also being observed when the driver is picking up something and looking behind. So what we can do, like we can actually capture such kind of signatures on the Range-Doppler heat map. Yeah. So the video got loaded. Here you can see that when the driver is loading, looking behind, some changes being observed in the Range-Doppler heat map. So apart from that, if we look into various other features like the Range-Doppler profile, the noise profile, or the range profile, what we see that for different kind of activities, that the kind of dangerous activities that the driver perform, we have different type of signatures in their feature pattern. For example, here it shows the distribution of these features for two different drivers. This blue is for driver 1 and the red is for driver 2. Now what you can see that yawning, using a phone, talking to the person in the left, or drinking, it shows lesser variation, and they are less dense towards the median, representing some kind of macro body movement of the driver. So what you can see that here, for this set of activities, the variation is high, right? So when the variation is high, that basically means it is a kind of macro body movements. That means the driver has significantly moved his head or moved his head, or there's a kind of significant deviation. But for kind of activating just by talking left, so the driver need not to move much, just turn his head or her head to the left and can talk, and this result in less variation in this profiling. Now, the thing is that, well, it's good that we can observe such kind of visible changes in signal properties for different kind of activities, but it is not very straightforward to develop a model out of it. Why that is so? Because there are multiple different research challenges here. One of the important research challenges that, say, whenever you are driving, you encounter with different kind of road conditions. So, for example, you might have a road bump, okay? And whenever you have a road bump, what we see that the signal property also changes. So, for example, here we have tried to capture the IMU signal as well as this mmWave signal. And here there is a sudden change in the IMU, indicating that there is a road bump, okay? And this IMU is placed on the dashboard of the vehicle. So it indicates that there is a road bump. And at that point of time, what we can also see a peak in the noise profile and the Range-Doppler profile. So that means this peak that we are seeing here in the Range-Doppler profile, that is not because of certain kind of body movement or explicit gesture pattern from the driver, rather just because the vehicle has crossed a bump, and because of that jerkiness, there was certain noise or certain irregularities that have been originated in the signal property. So this is one of the challenge that we have to deal with whenever we are going to build up a model. And another important thing is that what we see, like, we have actually taken all these range profile and the noise profile for this 16x64 two-dimensional matrix that we get out of these signal values. And we have total 1152 features. And if we just try to plot a TSNE embedding at a two-dimensional space, what we see that the dangerous driving, so these clusters, they show the normal driving behavior. Well, so for each of the dangerous driving, like anomaly in steering, drinking, fetching forward, nodding, they have somehow separable from the regular driving or the normal driving. Well, but for some activities, say for example, using phone, we still have a significant overlap between the regular driving and this abnormal driving. Well, so particularly when you have certain kind of micro body movement. Micro body movement is like your body movement is not significant. If your body movement is significant, if you apply the mmWave properties, your receive chirp should have shown a significant deviation from the transmit chirp, because of which you will see an peak in the IF signal, but that doesn't happen for this micro body movement. So the question comes that how you are going to detect such kind of micro body movements. So from this set of pilot experiments, the broad takeaways that we have are as follows. These features like Range-Doppler, noise profile, range profile, all of them show unique patterns across different driving actions and drivers. And what we see that each driving action has its unique signature, and the features of dangerous driving actions having micro body movements show close signatures of normal driving behavior, which is a challenge for us to develop the corresponding model. And in case of real driving, different road irregularities or the driving environment, like the road bumps or this sudden jerkiness at the congested area, that can also lead to variation in the feature space, and then that way they can confuse the model. So with this kind of takeaway, we developed a system like this. What we did that the broad system that we have built up, it has multiple different components. It has a pre-processing component followed by different classifiers. So for pre-processing, it captured a temporal variation and concatenate 10 feature frames together. And it takes two different data. It takes information from IMU as well as takes information from the millimeter wave radar. So the IMU is particularly to understand that whenever there is certain kind of road irregularities, we don't want our data to be noisy at that point of time, and we want to get identified at that point of time. And at the same time, we capture the ground truth data using the dash cam that we have mounted over. So we basically apply a min-max scalar to normalize the features from 0 to 1. And then what we do that we first remove the road-induced noise. So what are these road-induced noise? This road-induced noise particularly come because of these bumpy road signatures. Well, for that, as I have mentioned, that we take help of the IMU sensors, which are embedded within the device, and the z-axis acceleration of the vehicle is used to determine the jerkiness to road bump. And we filter the corresponding data to suppress the unwanted noise in the feature space. After that, we implement a classification pipeline. This classification pipeline contains multiple different classifiers, and these classifiers try to classify the dangerous driving from the normal driving. I will talk about this classifier in details. So we apply a two-dimensional convolution neural network, basically 3 such two-dimensional convolution neural network with valid padding and ReLU activation, and we use a global average pooling to extract these 96 feature embeddings, compute several cross-channel feature map which are helpful for subsequent model layers. So I'm not going to the details of this particular model. It is basically a convolution neural network that is being used. The interesting part is that we use 2 different classifiers here. One we call as the deviant classifier, and the second one we call as a DDB classifier. So this DDB classifier, which is the dangerous driving behavior classifier, it contains 9 neurons with softmax activation for 9 different dangerous driving action that I have mentioned earlier. And along with that, we have this deviant classifier that classifies the dangerous versus normal driving. So this entire pipeline is in 2 phases. That first, it finds out whether the driving behavior is dangerous or normal. If it finds out that the driving behavior is dangerous, then it classifies. It uses this DDB classifier to find out that out of the 9 different dangerous driving behavior that we have characterized, which one is being done. And interestingly, we use a lazy inferencing mechanism. Like in case of deployment, we do not run this DDB classifier all the time. Rather, we first run the deviant classifier only when the deviant classifier detects that there is a dangerous driving. Then only this DDB classifier is being loaded, and it is used to infer this dangerous driving behavior to find out that in which of the 9 classes this dangerous driving behavior belongs to. Now, coming to the implementation of this particular system, we have, as I 6843 ISK radar from Texas Instrument. Along with that, we have used this Nexar Pro dashcam along with an IMU for get the ground truth. And we also have a setup for acoustic sensing, which has been used as a baseline comparison to see that there are existing works on acoustic sensing for this purpose, to see that how acoustic sensing helps, or whether acoustic sensing works in this particular case. So we did the experiments on 3 cars with 5 different drivers. The distance between the driver and the radar was approximately 0.7 meter. And the important thing is that this, entire system is live in the sense that We have used the Raspberry Pi 4 Model B with 8 GB RAM, with which this particular device is connected, and all the inferences run on that RPi. That means you can have an embedded device that you can place within your car to do this detection. And what we believe that in the future, when this mmWave capability will come along with your smartphone, you can simply use a smartphone to do that inference, because we have tried to make the inference as much lightweight as possible so that it can be executed on the device itself. These are the details about the software and the tools that we have used. So we have made this entire implementation open source. So if you go to our website, you can even download the data that we have collected, and also you can find out the source code of this implementation that you can try out on that data to see. So I will quickly jump to the results, some of the results. So the first result basically shows the impact of the frame stack. Frame stack in the sense, like, as I mentioned, that I need to do the real-time processing. So it is always beneficial that if we can process on a lower amount of data. So that way, we try to understand that how many number of frames we need to fetch from the sensor, which can give me an optimal inferencing. Well, so that way I can reduce the processing load on the system, and I can actually run the entire algorithm on the device itself. I don't need additional hardware for that. So what we see that this is basically shows the weighted F1 score with different number of frames. We see that around 10 frames, this inferencing becomes mostly static, and after that there is not much change in the inferencing. So there is some minute change sometimes. So for example, with 16, you can see it is a little bit higher from 10, but that is a kind of marginal difference. But as I have mentioned that if I wait for more number of frames to do the inferencing, it slows down the inference. So what we found that this optimal number of frame stacking is 10 frames. That means you fetch 10 different frames from your millimeter wave sensor, and then you try to detect the activity. That works in an optimal way. Now, this is basically the performance of the classifier that we have used, and its comparison with other different baseline. So this fused CNN is the one that we have used, that is our model. Along with that, we have taken two other model like a random forest-based classification as well as a VGG16-based classification. And this shows the kind of confusion matrix for all. So what we see that this fused CNN, it provides better accuracy or better F1 score compared to others. So and this kind of performance we see throughout. And if we look into other modalities as well as the acoustic modality, which we have used as a baseline, we see that it gets confused for many of these activities, particularly for the micro activities. Finally, we have tried to look into the energy consumption in the system and how much resource and energy consumption it performed. So what we see that if we look into the power consumption, we see that the amount of power that is being consumed in this fused CNN model, it is less compared to this RF-based inferencing. Although this VGG16 has a lower power consumption, but as we have seen earlier, that VGG16 perform poorly in terms of accuracy. So there is this kind of trade-off. And if we look into the resource utilization, we see that almost 100% resource utilization, CPU utilization for all the three models. But if we look into the RAM utilization, fused CNN takes much less RAM compared to the other models. And that actually makes it suitable for running on the device itself. Well, so this is the kind of advantage that we get. So what we broadly see that using this kind of millimeter wave modality, we can pervasively sense the key activity features which are needed for driver's attentiveness. And what we believe is that this minimal invasive footprint of mmDrive, it could be a significant reason for it to mark its place as a practical and prominent commercial solution, irrespective of these video-based approaches that are used nowadays. And the system demonstrates an accuracy of more than 95%, which is quite good. And we have did the experiments in diverse scenarios and diverse with different drivers and environments, and we have seen that it works quite good. Well, so that basically conclude the kind of application that we developed with mmWave. I will also touch upon another application in short, but before that, let me see whether there is any question as such. Any question from anyone, or let me just complete the next part of it. Then you can take the questions. So the thing is that, well, we have developed an application, but how we can expand it further. Now, if you remember that initially when I started the introduction, I mentioned that we can use mmWave for doing a kind of multi-user activity sensing in a room. So, for example, you can have multiple different users within the room. Different people are doing different kind of activities. Some people are typing, person is doing an exercise, someone is sleeping, whether a single device can monitor all of them. And for that, we tried to develop an architecture of it where we mount a mmWave sensor with a servo, and the computation is being done on top of a Raspberry Pi. Again, we try to do the computation on the edge itself. And with the help of that servo, we keep on rotate this sensor to see that if we can track multiple users while they are performing multiple different activities. Now, we have certain interesting observation. So the first thing is that, so for example, if I try to localize individual people, so what you can see here, that here 3 persons are roaming in a roof, and if you look into the this range cluster, or what we call as the point cloud cluster that we get, we can see that there are 3 different point cloud cluster corresponds to 3 different persons. Well, so one point cloud cluster corresponds to 1 person, then second and third, and they keep on moving. So that way, if I just do a clustering and take that centroid, I can find out the location of this individual persons pretty easily. Then once I'm been able to track the user, next we see whether we can understand the activity of different people. Here also you see that the person is doing different kind of exercise, and corresponds to that I have different signatures in the Range-Doppler heatmap. Okay, so if you just closely look into the signatures, you will see that these 2 signatures, the one corresponds to this particular activity 1, and the one corresponds to the second activity. It's a bit different. Well, so for example, when that left is taken in front, then we see a different signature here. Then here it is like different type of jumping activities. So one case with a rope, and the second case the simple jumping. And here also you see that you see a different pattern here. Due to this continuous movement of the hand, you see a kind of peak which is happening here continuously. And here, when the person is just jumping, you see a change in the pattern. Well, now we move towards multiple user activity. When multiple users are doing activities simultaneously, here you see that one person is doing something, and at that point of time, when the second person crosses, we see 2 different. First of all, we see 2 different peaks in the Range-Doppler profile here. So when the second person enters, I get a new peak in the Range-Doppler, and that peak keeps on moving. So we can actually identify that how many users are here and the type of activities that they are doing. So here you can see that when the girl with this blue shirt, she enters in the frame, in the Range-Doppler pattern, here in the Range-Doppler pattern, some changes is being observed here. Okay, so this kind of changes we are able to observe. And finally, we see that, say, well, for these activities which are having significant body movement, we have nice pattern. But whether we can also see some pattern when the person's body movement is not significant, rather do some kind of micro scale activity. So, for example, just typing something on the phone or typing on the laptop. Here also you see, means although the energy of the heat map is not very high, but still there is certain pattern which is being observed. Well, and interestingly, if we just try to change the range resolution, we can see better energy concentration on this heat map, leading to a kind of prominent identification of the corresponding activities. So basically, all these kind of observation lead to interesting challenges on which we are currently working on, and which can be a kind of also food for thought for you. So what we see that there is a trade-off between this range resolution and the signal power, right? If you increase your range resolution, your signal power gets reduced, so you can identify the macro body movement, like when there is a kind of significant changes in the body movement. But for minor changes in the body movement, like the finger movement, you need to increase the range resolution. You need to decrease the range resolution and concentrate the signal power. Well, so the thing is that, well, can we continuously change the radar configuration to capture both kind of activities together? So, for example, if someone in the room is walking and doing some exercise and some other person is typing, whether I can use a single radar to detect both simultaneously. And if I have to change the radar configuration for that purpose, how quickly we can change the radar configuration, right? Then, whenever we are sensing the activities from multiple subjects, the similar type of questions like how quickly we can identify the activities. Well, and finally, the important thing is that say whenever we are identifying individual activities for individual user, can I differentiate the users or can I uniquely identify individual user? Whether any kind of fingerprinting possible. So, for example, I, Sandip, I perform certain activity, go out of the room. After 10 minutes, I come back and start performing another activity. Can the system identify that whether Sandip has performed the same activity or this person is actually Sandip? Right? So these are the kind of very interesting research challenge towards using this millimeter wave sensing for pervasive applications. And there are multiple interesting open problems that can be taken up for further research. Well, with this, I would like to conclude my talk here. And thanks to my students who are currently leading this project. Orgo is a research scholar at our team. Anirban is a postdoc. We have an undergraduate student, Abhijit, who is working with us, and my collaborator Shadhin from Cisco Meraki at US. And before I stop, just a kind of broad overview of our lab. So it is a young system research lab in India that started in 2022. Currently, 4 PhDs have been graduated. They are placed in, interestingly, all of them are placed in industry, one in Nokia Bell Lab, Cambridge, at Intel Labs, TCS Research and Innovation, Ericsson Research. And one of the graduate students who is going to graduate soon, he will be having its own startup. There are multiple internship and postdocs, different research institutes across the globe, and we are continuously having good publications in this space. And we are working on different aspects of sensing, not only on the millimeter wave sensing, but we are looking into sensing through wearable, sensing through acoustic, even for this sensing through video or that kind of modalities, to look into that whether we can develop pervasive applications for accessibility or assisting the kind of mankind. And before I close, kind of shameless advertisement. We are having multiple open positions at our lab. If you are interested, you can get back to us. You can write me. Also, we are having taking regular internships, both for the undergrad, graduate, and the PhD students. If you are interested, you can drop me an email. So that's all from my side. Thank you for your patience and giving your time listening this. If you have any further questions, I will be happy to take it up. Thank you.
Thank you, Professor Chakraborty, for an informative talk. If there are no questions, we can close the session here. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box, and the link to the recorded video and slides will be posted on our webpage. Thank you and have a great evening.
Thank you. Yeah, bye.